Yes, so it has started recording. So here in today's class, we are going to discuss this common emitter amplifier circuit. Huh? So common emitter amplifier last class also we have like what we have discussed, that was also a common amplifier circuit only. Maybe if we can go back to that. So we have also see this is also an CE amplifier only, right? But the difference was like here we need a separate VBB one battery to bias this base terminal, right? But we have seen earlier in our DC biasing case that we could have also used this VCC to bias this base terminal, right? Like by voltage divider biasing. That is one that we are going to do for that change here, right? One more thing is that we have also mentioned this thing that we generally do not keep the signal source and this DC source in series, right? Because we do not want this current IB to be flown through this VAs. And the other thing was for this VAs, generally one terminal used to be grounded, right? So for all these things, we are not going to use this type of configuration to make one amplifier, but rather we are going to use this type of configuration, okay, where you can see this is VCC, this is RC, this is that NPN transistor. So here we have used two resistances R1 and R2. You know that voltage divider biasing. So we are biasing this base terminal by these two resistance, by using these two resistance, right? And the signal source has been isolated from this DC supply by this capacitor, which is also called the coupling capacitor. And you know the function of this coupling capacitor, that when you are analyzing the AC part, this capacitance, you have chosen the value of this capacitance such that for this signal frequency, you can treat it to be a short circuit. Right. So for DC, it is open circuit. So when you are doing the DC analysis, this part is not there. When you are analyzing the AC part, then you have to consider this capacitance to be a short. Right. So to do that, how should we proceed? Right. First thing is that, like, how to do you have to do the DC analysis, right? And that is quite straightforward. We have also done it during the DC analysis part. So it is quite straightforward. You have to just remove, this part, just remove this part and only do the analysis of this part. You have to use Thevenin and find VTH and RTH, and then try to find IB, IC, and all these things, V of C, right? So you'll get the DC part. So you're not focusing on the DC part here again, but rather what we are now focusing is on the AC part. Okay, so let us try to draw the equivalent, AC equivalent circuit. Okay, so what will be the AC equivalent circuit? So you know that for to make this AC equivalent circuit, all these DC sources, voltage sources has to be grounded. So that way, this R1 and R2 now should be connected with ground. So you can see that we have done that. And other things will remain the same, and this capacitance would be treated as a short circuit. So that's also you can see from here, right? So this is now the AC equivalent circuit, and here is this transistor, right? Now, to do or to calculate what is the small signal gain, we have to draw the small signal hybrid pi equivalent circuit, right? Small signal hybrid pi equivalent circuit. So how to do that? So first, what we have to do, we have to draw the small circuit equivalent circuit for small signal equivalent circuit for this transistor itself, NPN transistor. So you already know that the transistor would look like that, and here we are also considering R naught, means the early effect, right? So this R naught is already been here connected, you can see, and this is a base emitter and the base collector and emitter terminal, right? And let us now see what are the other things that we have to do here now. See, with this, right, with this collector terminal. So with this collector terminal, this RC is been connected and the other terminal of RC has been grounded. So we can write this, this is RC. And if we say like this emitter is also grounded, if we say that this is grounded, then the RC is connected here and the other terminal is grounded, right? Okay, what about R1 and R2? So if you look from here, from this terminal, so they have a common terminal here and both terminals, the other terminal of both resistances are grounded, right? So you can replace both of them by an equivalent resistance, right? And the further equivalent resistance, the one terminal is connected with the ground with this base terminal, other terminal would be connected with the ground, right? So we are replacing this R1 and R2 with their equivalent resistance. So you know that they are in parallel, right? If you look from here, so basically it is R1 and it is R2, right? And it is this base terminal, right? These are both are grounded. So the equivalent resistance, if you look from here, it is R1 parallel R2. That's what you can see from here. And with this base terminal, you can see this RS has been connected. That is the resistance maybe from this signal source, or you can also use, if you want, some external resistance before applying the signal to this point. And here you have this VS, right? So this is what the equivalent circuit would look like. So is there any doubt like from how we are getting from this total circuit to this AC equivalent circuit, and then we are getting
Sir,
a small signal equivalent circuit? Yes, yes, please tell.
sir, the RC would be grounded, sir. RC,
Huh.
RC and RG.
RC other terminal would be grounded, na? Because for AC this VCC would be grounded, right? You recall that yesterday we
Yes, sir.
discussed
Yes, sir.
this is VCC, na?
Yes,
So you
sir.
have to replace this, then it will be grounded, na?
Yes, sir. Sir, means in this we means will we close the circuit or we will leave it open?
Which circuit?
Sir, the bottom circuit, sir. Like we have closed the RC and R not part. So we will leave the RC open or will we leave it closed?
No, no,
So
no.
like we did yesterday,
Yes, sir.
we will connect RC to a different ground.
Yes,
Right.
sir.
We will put RC to a defined ground if it is like if it helps in your understanding. Okay. But
Yes.
ultimately, there is no physical difference between one ground and the other ground, right? But
Okay, sir.
okay. But if it helps for your understanding, you can consider different grounds. Okay. So there is no doubt, right? How we are getting from this circuit and this small signal equivalent circuit. Okay. Now the thing that we have to do, we have to now calculate what is V output, and if you know what is V output, then obviously we can find V output by Vs, that is the small signal gain. Okay, so can you tell me how to find? This is straightforward only, right? It is not difficult. Okay, anyway, we are doing it. So first we have to find what is V pi, right? Because if we do not know V pi, then we cannot find what is the current here, right? So let us find what is V pi. So from here, it is quite easy, like it will be just simple voltage division, right? So for that, V pi would be the, you know, this divided by Rs plus R1 parallel R2 parallel R pi into this Vs. Please check, is this correct? So this is the equivalent resistance of this part. This is the equivalent resistance of this part, right? And it is basically a voltage division. So voltage drop across this equivalent part we are finding. So this is basically V pi. So if this is V pi, now we can find what is V output, right? So what will be then the V output? V output would be equal to this Gm V pi into, now here these two resistances are in parallel, right? So it is R naught parallel RC. Right. So that way you can find Gm into R naught parallel RC. Now we are putting the value of this, we writing the value of this V pi, right? This is R1 parallel R2 parallel R pi by R1 parallel R2 parallel R pi into Vs, right? So this V naught by Vs, which is nothing but this gain. Gain means again here in the small signal gain. Huh? Small signal gain, that would be equal to, I think I am missing some minus sign, right? I have to correct it. Huh? So it is R1 parallel R2 parallel R pi divided by R1 parallel R2. I think here also I missed one part, R pi plus here you will have this RS as well, RS plus here it is RS. Now the thing is that if you know this V output, right, this current flowing like this, so it will cause a voltage drop here in this polarity, but we have considered V out to be like this, so we should have put a minus sign here. So that way you can see this. If you know this, now if you know, if you can analyze the DC part of this circuit, then you can find the small signal parameters. For example, GM, you will find R pi. You can also find R naught, and RC and other the resistances would be given to you. Then you should be able to find what is the small signal gain of this particular particular amplifier, isn't it? So is there any doubt in this calculation? No, it is quite straightforward, right? Okay. So now here a couple of things. 1 minute. Yeah, please check. Is my screen still visible?
Yes, sir.
Yes, sir.
Okay, thank you. So sometimes we have to also find what is the equivalent input resistance and output resistance of a particular amplifier. Okay, so if we say like input impedance, then basically input impedance means if we look from here. Okay, maybe I will choose a different color, maybe red would be a fine. Right, if you look from here, the resistance, if you look from here, the resistance that you will be able to see, that is called this input. If it is, here it is only it is only resistance, so that's what I am writing R in. But in general, it's better to say like it is Z in, right? Input impedance. Okay, so how to find this input impedance? And similarly, if we have to look in the output from the output side, then we will also able to see what is the output impedance of this particular circuit, or this is Z out. Okay, so to find this input impedance, input and output impedance, or there sometimes it is also written as the input and output resistance. In many questions you will also find that. Right. Now, how to find that input resistance? Okay. So when you want to find the input resistance, then first what you have to do, you have to just connect one. There are a couple of ways by which you can do that. One way is that you simply connect and get a known voltage source here. Known voltage source here, and then you find what is the current here. Okay. So if you apply suppose 1 volt and then you are able to find what is the current, then basically current by voltage by current will give you the equivalent resistance, right? So are you getting what I am trying to say? Okay, maybe I will draw it here. So here it is, eventually you should not do this because it is by seeing only you should be able to tell this. Okay, so it is basically this R pi. Now here what you can add a known voltage. Okay, say we are adding Vx, right, and then we have to find what is Ix. Okay, so if this is known and you are able to find Ix, right, then Vx by Ix will give you the equivalent resistance. Here it is quite straightforward. If you look from here, the equivalent resistance or R in is would be like this R1 parallel R2 parallel R pi, right? You should not do this process here, right? Because it is quite straightforward and you can see it. So this is the input resistance if you look from here, right? What about the output resistance or output impedance? So
Sir,
again,
sir, isn't RS included in the input resistance?
generally RS is to be considered as like included in this part. Okay, this is a good question. You have asked. Generally, RS base been considered to be included within this source. Okay, generally RS, we generally do not apply, I mean, use this RS as an from our side as a user point of view. Generally, this RS is the source resistance that is offered by this signal source. Okay, to show that it has a resistance, we are putting this RS separately.
Okay, sir.
Okay, so this Rin is, I hope it is clear. Now, what about then this R naught or this output resistance? So almost the same thing, but when you do find our output, then what you have to do? First, deactivate this VS, the signal source. So when, because, or deactivate means you replace this VS by its equivalent by its equivalent circuit component. Means if any voltage source can be replaced by its equivalent circuit, means it is basically a short circuit, right? Voltage source. So basically then you you have a short circuit here, then you have an RS here, then you have this R1 parallel R2, then you have this R pi, then you have here this GM V pi. Just I am drawing the complete circuit first. Then it is R naught. Then you have this RC, right? Then it is quite straightforward. If this voltage is 0, then V pi is also 0. If this V pi is 0, then this is also 0. No current. That means it is again open circuit, right? This current source is open, right? So that means this is, you can just remove this part from here, right? Then you have to look from the resistance, which is from this side. So if you look from the resistance, again, it is quite straightforward. You can do the similar analysis, putting an voltage source, finding the current. But if you look from here, it is quite easy to understand that the equivalent resistance would be, or equivalent output resistance would be this one only. Yes, you have a question?
Yes, sir, it got cleared, sir.
You got doubt? Okay. Okay, fine. So like that, you can find what is the input, what is this input resistance or input impedance of an amplifier, and what is the output impedance of an amplifier. Now you might be thinking why these parameters are important. Okay. So quickly we can discuss that. So the importance, okay, the importance are, suppose let me take this amplifier as a black box, okay, for the time being. Okay. So say this is that amplifier. Okay. Now you have a signal source. Okay. Okay. Maybe I will also put the signal resistance here. No? This is RS. Now you understand what is RS, right? RS is primarily the resistance offered by the source, right? And here you have connected with the load, RL, load resistance, right? Now you see, you are now calculating, or you are now trying to understand why this R in and R out is important. So let me point it out again here. R in is the resistance offered by this, R out is the resistance offered by this, right? So see that from here, this is the signal source, right? The signal source is not very strong, right? For example, if this is suppose an radio signal that you are receiving, then its amplitude is very small, right? And you want whatever the signal you are receiving in your antenna, you want the total thing to be fed into the amplifier. Are you getting my point? The total thing to be fed into this amplifier, total thing. That means you want much less drop across this RS, which is offered by this resistance only, right? You want the total thing to be getting across here. That means in the context of a bipolar junction transistor here, that means you would like to have, what you like to have is that the entire Vs would be drop across this V of BE. Again, small v, small b, small e, right? That's what I'm saying. Because if this signal, the more signal will fade here, the better would be the amplitude, or the better would be the amplification, right? Right, so that's what you want, like to the entire signal, if whatever is possible, to be dropped across this V of BE. So for that, what should happen? For that, you should obviously it should be obvious to you, right? That the R in has to be much higher than this RS, right? Then only to say again simple voltage division, right? The R in is expected to be much higher than this RS. Then only this most part of this VS will be dropped across this amplifier. Right. Okay. Now let us see what from the output point of view. Now, if you consider from the output point of view, this transistor has an resistance at the from the output side. It is R naught, right? And it is RL, right? Okay. Now here it depends, in different ways. For example, in some, in okay. Now tell me, what do you want from this R naught? Do you want R naught to be as high as possible, or R naught to be as low as possible? Any idea?
High, sir.
High. Why high? Can you explain?
Hi, sir.
Sir,
Okay.
because
Hmm.
as we see, V output upon Vs depends on R naught,
Um,
RSC.
that no. Here, see, okay, you are okay. So say the gain is been fixed. Okay, you cannot do anything on this gain. Okay, say the gain is fixed. Okay, so gain is fixed means okay. Say that R1 R naught is also fixed. Say okay, let us vary this RL. So what you will want? What you want? You want RL to be higher
Sir,
than R
how
naught?
is
Hmm?
how is R naught fixed when we are wearing RL?
When you are varying RL, okay, RL is the external
Okay,
load, right?
okay. Means
Right.
after RC. Okay, okay,
Huh.
sir.
RL is external load, right? Okay, so if you now consider this to be this amplifier like this, okay, then you have, I mean, at the output side, you have a voltage source which is being amplified, so A of Vs, right? And you have this output resistance which is R naught, and you have this RL here. Now, is that simplifies the thing? Now you see, you want the most of this voltage to be dropped across this RL, right? You do not want much drop across this R naught.
Sir,
So
R naught and RL shall be parallel, right?
R naught should be
Yes, sir.
R naught is parallel with RL. Again, it depends on which type, which way you are making this transistor. There are different types of transistors. One is called this conductance amplifier, means trans conductance amplifier. One is called the trans resistance amplifier. So depending on that, means okay. Again, but
But from the equivalent circuit we are considering, we can see that R naught is parallel to RL.
from this equivalent circuit, yes, from this equivalent circuit, we can see R naught is parallel to RL. Okay, true. Okay, even from this equivalent circuit, if you are considering this type of amplifier, okay, then also can you make a comment? What you you want RL value to be higher or lower?
Sir, if RL is lower, then most of the current flows through it.
Is it the current that is important here, or is it the voltage that is the signal that you are referring to that is important to you?
So voltage should be same across both R naught and RL since they are parallel.
Yes, but how does this the value of RL would impact now?
Sir, RL should be very high.
RL should be as high as possible, because if you make this RL small, then what will happen? See, if you're considering this amplifier, the entire thing is in parallel, right? So if you reduce the value of RL, so the total output means the total resistance here that will fall. So the overall V output will fall down, right? So you want RL to be as high as possible.
Sir,
Yes.
excuse me, sir. Sir, here AVS, I mean amplified signal is always constant, right? I mean it is independent of this RL.
This amplified one.
Yes, sir.
Well, that is not very true, because see, here, if you are considering output from here, right, then you are getting this gain to be like this, right, in this way. Okay, so suppose now if we have added, if we have added, which color I can choose, okay, and resistance, which is like this RL, probably in the next, let me check, maybe not even in the next, but in some example we will do definitely this type of example. Suppose if we add one RL, then what is going to happen with this RL? Now this RL, you see, this RL will be in parallel with this RC. Then if you are calculating V output, then you cannot eliminate the effect of RL, right? So if you want to find what is only this V out without this any load resistance, then that is one thing. But if you are trying to find the V out in the presence of RL, then obviously the output or the overall gain would be dependent on RL as well. Then if you do not want that gain to be dependent on RL, then you have to mention that you are considering that you are considering the amplifier when there is no load, right? But if whenever you are connecting one load, the overall gain has to change. But the whole point from here was to discuss only one thing, is that like from here you can see this R in has to be much higher than this R is. That means the input resistance of an amplifier is expected to be as high as possible. Similarly, the output resistance of that amplifier to be a bit low as possible. Otherwise, what will happen? Otherwise, most of the drop will fall across, means you will not be able to transfer the maximum of the output voltage to the load. Okay, again as I have mentioned, this depends on which type of amplifier you have designed. There are different types of amplifier. One is called voltage amplifier. It can be a current amplifier, it can be a transconductance amplifier, it can be a trans resistance amplifier, couple of things. But I think you will agree on me that if it is from this, I think there should be no doubt from this input side. And
Correct.
if the output is suppose in the output section, if you are getting the output like this, right? If the output equivalent circuit, we are not going much more detail inside of this circuit what is there, but if the output portion, if you are having a circuit like this, then in that case you want that RL to be much higher than this R0. Yes, you have a question, please.
Sir, in the parallel case, if we
Ah.
consider, sir, we are interested in power transfer, right? More than voltage.
It depends on it also depends on yeah, you are getting the power transfer. Yeah, true power transfer, right? Yes, then
Sir, you are not audible.
hello, can you hear me?
Yes, sir, we can hear you.
Yeah, I think there's some network issue from your side. Okay, so I think if you have understood this part, and how to analyze this type of basic common amplifier circuit, then it is fine. And here only one thing I want to mention. If you see that what is the if you comment on the stability of this particular circuit, then I think during DC biasing also we have mentioned, as we do not have any emitter resistance, so there is no feedback loop, right? No negative feedback, right? So as there is no negative feedback, so if you first this circuit is not very stable. If you replace this transistor with another transistor, that means with respect to the change in beta, this circuit is not very stable, right? You recall, right? When you have a resistance here, then we have seen that, right? Then you also, if you have a large change in beta, then also this circuit will not change its performance much, right? That is one thing, very important thing. Other important thing is called the effect of temperature. Okay, please try to understand what is the effect of temperature here, right? For example, suppose now this transistor earlier was operating at 20 degrees centigrade. Okay. Now suppose the temperature has rise to ambient temperature has rise to 40 degrees centigrade. So ambient temperature rise. So that means this junction temperature also rises, right? Both junction temperature. And you know, when you have studied diode, what is the effect of increasing the junction temperature? When you increase the junction temperature, reverse leakage current increases of any PN junction, right? And when the reverse leakage current increase, the forward current has to increase, right? Because you recall diode current equation is Is into exponential of that part. So if Is increases, then the forward current also have to increase, right? So that way, suppose when the temperature has increased, so here this junction, BE junction, that temperature has increased. That temperature increase means the current of this BE junction has increased. That means IB has increased. So when IB has increased, IC will increase, right? So if IC increases, please try to follow me. If IC increases, okay, then what will happen when the IC has to flow through these junctions only, right? So this is the, okay, if you consider this is an NPN, this is the depletion layers that are there, and when the current will flow, even though these regions are heavily doped, right? Base region is not that heavily doped, collector is also not that heavily doped. So you can consider this region to be, this region will offer one resistance, right? Right. So if the current increases, then more voltage will drop across this. More voltage drop means what I want to mean, the I square R drop, right? More drop will occur across this transistor. So more the drop across this transistor, more would be the power dissipation, means the temperature will further rise. So once again the temperature means the temperature will again rise. Now as again the temperature rises, again this junction temperature increases, right? Junction temperature, that increases IB, that increases IC, again that IC will increase this again the temperature, right? So that means once the temperature increase, the circuit will try to fall in a positive loop, positive feedback loop. Positive feedback loop means, see, the current is continuously increasing, right? Because of this, and one point of time what will happen, the current will be so large that you know that every transistor has its power rating, right? Like diode. So if you cross that power rating, the transistor might burn, right? And the same thing can also happen if your transistor, if you are using suppose very high power transistor, but the same thing can happen with the resistor as well, because IC is flowing through this resistance, right? So if you are using a low wattage resistor here, then this is before your transistor burns, this RC can also burn, right? So to avoid this issue, we should also introduce some negative feedback here. Okay, and the negative feedback can be introduced by introducing the emitter resistance RE, as we have discussed earlier, right? And this particular effect due to the increase in temperature is called this thermal run away. Okay, and this is quite type of destructive process, that once it falls in this loop, the temperature of this circuit transistor will keep on increase, and if you are not able to control the temperature, that at certain point there is a chance that transistor might burn. So I hope that thermal runaway, that effect is also clear to you. So use of this resistance RE will help in this reducing this thermal runaway. At the same time, it will also help you to stabilize the transistor Q point in terms of change in beta. So in the next page, we will try to do the similar thing. Means we are trying to analyze and circuit which is we are trying to analyze one circuit. Okay, here where we have used this RE, right? And when you have introduced this RE, the analysis, the small signal analysis, you will see yourself that this will change slightly. Okay, and it will become bit more complicated. Okay, let's see that how it is changing. So again, to do the small signal analysis, first we have to draw the small signal equivalent circuit, small signal equivalent hybrid pi model of this bipolar junction transistor, and that has already been drawn. So you can see emitter, base, collector, and for this particular analysis, we are assuming that VA is very high. Okay, so VA is like, we are assuming that this VA is very high, right? So that way R0 is also very high. Okay, and when this R naught is very high, we can actually neglect that, because you see from here, this R naught will come in parallel with RC, right? And so it is in parallel combination, right? So the in a parallel combination, the resistance will be determined by the resistance of this lower, I mean by the lower resistance. So right, so that way we can neglect R naught. Okay, and also that will simplify our analysis. See from here. So we are not considering R naught here. Okay. So then this is the equivalent circuit. Now what else? We have RE with this emitter that is connected. So we will write this RE. Okay. What else now? And, in this okay. Now if you consider from this base side, then again R1 and R2, they are in parallel and they are connected. One terminal is connected with base terminal, other terminal would be grounded, right, as earlier. So one terminal is connected with the base, other terminal is grounded, and emitter terminal after RE, it is also grounded. So this is grounded. This is R1 parallel R2. This is also grounded. Then we are doing the AC analysis. So CC can be considered as a short, right? Then we have this RS. Then we have this VS, that is the supply voltage here, right? And what about in this output side? Here we are taking this output. We have this RC connected, one terminal with the collector, other terminal is grounded, so it is RC, right? And it is basically the V output, right? So this is actually the total circuit, right? The total small signal equivalent circuit. Small signal equivalent circuit, right? Okay. Now you see, the compared to the previous case, the circuit is now a bit different, right? And you also see the analysis will be also different. And here, and if you have noticed one more change, in earlier case we have used this here GM Pi, right? We have considered two different models. One is with GM Pi and the other one is with this IB and beta IB. So here we are using this beta IB, and I think you recall the reason why we are using this, because here it would be easier to find IB rather than find this one. But anyway, I'm not saying you cannot use the other one. You can use that. But if you use this IB and beta IB for this type of case, it would your analysis, your analytical work would be less. Okay, so now let us start with that and try to find what is what is this output versus in output by input, that is V output by V naught by Vs, that is a small signal gain we have to find. Okay, so for that, so let us start and do it step by step. So let us try to first find what is V in. Okay, V in is the, if you look from here, what is the voltage drop? Okay, if you look from here, that means voltage drop between this point and ground, right? So if we know this voltage drop, the similar drop will also occur across this, right? The similar drop will also occur across this, right? Okay, so we can write it here, this V in. So what is V in? So V in, this IB current is flowing through this RB, and here beta IB current is flowing through this one, right? And both of them will coming here and flowing through this RE. So it is basically 1 plus beta of IB, right? So we can write it as this IB R pi plus IB plus beta IB into RE. So basically, see, then what we are doing, we are trying to find the voltage drop across this. The voltage drop across this is same as the voltage drop across this. And here we know IB, so we are writing V in terms of this IB, right? So we are writing here this IB R pi plus here 1 plus beta, and here this RE, right? Then it would be easier if we now also try to find what is the equivalent resistance, if we again look from here, so we'll say it as R in. Okay. Why we are doing this, it will be clear to you just in 1 or 2 minutes. So it is R in, or let us say this R in 1, maybe R in 1. Okay, R in 1. So it is R in 1 is equal to, so how can you find R in 1? Guys, how can you find R in 1?
We connect the voltage source.
Just a small change. Yeah, that is one way, but that process, I think we should, means we do not have to do it right now, or maybe the similar thing we are doing. Okay, see here, we are R in 1 is not that. R in 1, we are defining this one. Okay, we are trying to find the equivalent resistance if we just see from here. So what is this R in 1 then? See, R in 1, here we know the voltage, right? We know, and we know the current, what is flowing from this, right? So if you look from that, it is basically voltage by current, right? So it is basically V in by IB, right? And that if you do that, so it is basically V in by IB, right? So you will get 1 plus beta into RE. Is that clear? If you try to find what is R in 1, right? Okay. Now we'll define one more resistance, but that resistance is now from this side. This is R in input resistance 2. Okay, so what would be this input resistance 2? R into, see, it is nothing but, now you are considering that from here to here, the resistance is RU1. And you have one more resistance which is in parallel with this, whose value is R1 parallel R2, right? So it will be R in 1 parallel R1 parallel R2. Is it fine? Right?
Yes, sir.
Okay. Now let us try to find what is V in, because now we know what is R in, right? So we can find V in. V in means the drop between this point and this point, right? In terms of RS, R in and VS. So V in is equal to R into divided by R into plus RS, this resistance, into VS, right? So we know now what is V in, right? What is V in terms of this VS. Okay. Now again, see this. What is V in? V in is the voltage drop across this. So that V in is the voltage drop across this, right? And we are able to connect, means we are able to relate this V in with this VS, right? With the known parameters. Okay. Okay. Now, what is V out? If you have to now suppose find what is V out. What is V out? V out is equal to minus beta IB into RC, right? Okay. Now, we have to do some manipulation so that now we can replace, say IB with this V in. Okay, because if we are able to replace, IB with V in, then in place of V in we can write VS, right? Then we will get V naught by VS. I hope you got my point, right?
So from the first equation, we can replace IB.
Right. So we will write it here. So here it is beta RC, and here it is. Okay. Can you please then guide me? What should I do? This is beta RC. This is beta RC. Okay. Then what else? You are putting the value of IB. Please
So
tell me.
V in upon R pi.
V in upon
V in,
RN1.
V in by
R pi plus
1 plus
beta
beta,
into RE.
1 plus beta into RE. Then That's all.
Yes, sir.
Okay. So if this is so, then after that, okay, we need some more space. Okay. Then after that, what should we do? This is beta RC. Now, in place of V in, we have to replace this V in with this VS, right? So let us do that. This R into by R into plus RS into VS. Then here we have this term as well. 1 plus beta into RE, right? Okay. Then we have this term V output by VS. And what is the value? Beta RC divided by R pi 1 plus beta RE into R into by R into plus RS, right? Okay. Now, couple of conditions. Okay, so this is basically the small signal gain, right? So this is without any approximation, right? If you can find this IR2 or then this the small signal parameters, for example, R pi and beta value is given, then you should be able to find what is the gain of this particular amplifier, C amplifier with emitter resistance, right? Now, see, if we say for this particular case, Ri into is much greater than Rs, right? We are choosing the value of R into. R into means where is the value of R into? Means we are choosing the value of R1, R2 and R in 1. R in 1 means Re and beta, such that this condition is satisfied, and in most cases the source resistance is quite not that high. So that way generally R into is always much greater than Rs. So that way you can see this is R into by R into plus Rs. So this is much higher. So you can neglect this. So it is R into R into. So basically this whole term become 1. So you can neglect this term, right? So then this term become beta RC by R pi plus 1 plus beta RE, right? After this, okay. Now here we'll try to do one more assumption, and the assumption is 1 plus beta into Re. We are taking some value of Re and it is multiplied with 1 plus beta. So this become a quite a large value, right? And if this is higher than much greater than this R pi, then here you can see you can neglect this R pi, right? And also this assumption is quite valid that 1 plus beta can be treated as a beta, right? That way you can also neglect when you can also consider like this two cancel out, and the overall gain can be approximated. I should better write it and like approximated to this simple expression. It is basically nothing but basically minus RC by RE, right? So here what you can see that the total small signal voltage gain is also independent of beta, right? It is primarily dependent on the value of this RC and RE. So it is not dependent on the value of the transistor, means which transistor you are using, right? And for that, these conditions has to be satisfied, right? These two conditions has to be satisfied, right? Is this part clear to all of you?
Yes, sir.
Okay. However,
Sir, here we are choosing R1, R2, and RE. All are higher. I mean, high in value, right?
We are actually our conditions are like here these two, right? You know, for that whatever should be the value of R1, R2 and all these things. So maybe you can individually, if you want to check, you can check it individually to have a higher IN2, that is this one. So obviously it is expected that R1, R2 has to be higher, and also R in 1 has to be higher. So to have RE1 higher, so here you can say this R pi, but it is in series with this R pi, RE, and this means you can say like, like it is up to you, how you are going to make this RE1 higher. Okay. But here, if you see from the second condition, it is 1 plus beta of RE is much, much higher than R pi. So obviously, we would try to make this RE bit higher, right? Means from this REIR1, you will want this term to be higher than this R pi, right? So that means either beta value is higher or RE value is higher. So you can choose with RE value higher, right? But see the drawback. If you have the higher value of RE, then RE is sitting in the denominator, right? So that means the gain actually reduces, right? So whenever you are introducing this emitter resistance, your gain falls. Your gain falls down. Okay, and eventually you can also compare this gain with the previous this gain here. So you can see from here. Here the gain is GM, GM into R naught RE, then plus this, right? Here also you can do some assumption and say that RS is much higher than this. So that way you can neglect this part. But you can see the gain is dependent on this GM in parallel with this R naught and R by into RC. So if you now calculate this gain, okay, we will do one analysis, one example, okay, with this gain without considering RE, then we will see that here the gain is bit higher. But whenever you are introducing this RE, you will see that the gain actually falls to a good amount. Okay. But that is that is again there is a compromise in the sense that because this circuit is much more stable, as I mentioned, compared to the previous circuit, but with a disadvantage that the gain reduces. Okay, right? Gain reduces. Now, can you think of any way to increase or enhance the gain without affecting the stability of this particular circuit?
Make RE small.
Make RE small, okay, but that will impact the stability, right?
Good.
So we can increase RC.
We can increase RC, okay, we can increase RC. That is one way, but again, that will try to negatively impact the V of CE, right? Because now this point is, see, it is not very difficult because this gain here, when we are considering this gain is a small signal gain, right? So if we have a suppose one capacitor connected in parallel with RE, then for DC this capacitor is open circuit. So for DC, RE will provide the stability, right? However, when you are considering the AC analysis, then due to this capacitance, this portion would be grounded, right? Due to capacitors, right? This would be grounded. Then this effect of RE would not be there. So you will be getting, so your entire analysis would be similar to the previous analysis, right? That way you can, remove or you can actually do an improvement on the small signal gain. Okay. So I think it's already 11. You have class already, right? So we'll stop here, and in the next class we'll again start from here. Okay. So yeah. So if you have any doubt.
So can you repeat that last part again?
Last what? Last part or?
So this
When you are
capacitor one.
grounding the emitter.
Oh, capacitor. Okay. So suppose here if you have used one capacitor, connected one capacitor, right? Then during DC analysis, this capacitor would be open circuit, right? So during DC analysis, this RE is present, right? So and this RE will give you the stability, right? In terms of that beta change in beta in terms of increasing temperature, right?
Sir,
Hmm.
sir, if it is an open circuit, okay, yes, sir, understood.
Right, mean this capacitor is open circuit, means RE is here, right? So you have to just simply remove this RE, see, remove this capacitor, right? See, you have to just remove the capacitor. You have to, like, as if the capacitor was not there in DC. However, when you are doing the small signal analysis, then what will happen? This capacitor can be treated as a short circuit. So that way, this capacitor other terminal is grounded. So that means you can say like this terminal is also grounded. That means emitter is now grounded. So emitter is grounded means this line is grounded here. This node is grounded, right? Then the entire analysis would be similar to like this analysis. I mean, similar to this small signal analysis, isn't it?
Okay, sir. Okay.
Sir, sir, but in the absence of RE, sir, shouldn't it negatively impact the circuit?
That's what we are not removing RE. What we are doing, RE is there, but in parallel with RE, we are connecting one CE. So basically, the circuit is something like this. Okay, let me. Yeah, I think if you have a class, right? So please, those who have a class, please feel free to leave and join the next class. Okay, this is because you are asking, so we are drawing this circuit. So the circuit would become now like this. This is R1, this is R2. This is coupling capacitor, this is RS, and this is this VS. Okay. Is this clear to you, this circuit?
Yes, sir.
Okay, so now what I am saying is that during DC analysis, right? During DC analysis, what will happen? This capacitor will not be there, no? Because this capacitor will offer an infinite impedance, right? Infinite impedance in parallel with some finite impedance. That means overall this impedance would be, means this resistance would be there, right? So you do not have anything. So during DC analysis, this RE will provide the DC stability, right?
Yes, sir.
You understand, right? However, when you are considering the AC, then what will happen? During AC, this capacitor will behave as a short circuit, right? So this capacitor is now shorted. So you understand? So this is now shorted with this during AC analysis. So that means this point is already shorted, right? Then what is the point of keeping this RE during AC analysis? Remember. So during AC, this is also grounded, right? This is now shorted. This CC is now shorted, and the equivalent circuit is like this. And you can do the analysis and see this circuit is now exactly similar. This AC equivalent circuit is exactly similar to this circuit.
But sir, we are considering small signal gain, right? Then what is the use of adding? Means in case of small signal gain, both the circuits are same. Then how will it provide stability? Because RA is not considered in both of the AC analysis cases.
Yes, but what we are, again, please try to understand what we are trying to point out is that we are saying during DC analysis, this RE would provide the stability. You recall that when we are considering this biasing part before we have started the amplifier, then we have considered that if you now replace this transistor with another transistor, due to the change in this beta, right, the Q point will change, right? So that was during DC analysis.
Sir? Sir, is the phenomena of thermal running only takes place in DC part?
So it can actually take place even in AC. You are right.
Sir, so here in AC part also RE is providing some sort of stability, right?
Yes, yes, you are very right. I thought I will take it up in the next class. So for that, maybe what you can do, you can probably do one more way. You are right. Very good point. So now we have changed the circuit little bit more, right? And what we are doing, we are splitting these two resistance are this RE into two parts. One is RE1 and other one is RE2. This is the coupling capacitor. This is RS and this is VS, right? And here it is VC. So here we will add one capacitor, but the capacitor we will now add only across this RE2. Okay, so that during AC analysis, this RE2 part is grounded, means this part is grounded. So only the effect of RE1 would be considered, and RE2 is higher than RE1. Okay, so that way this part will provide even the AC stability. Okay, but for DC stability, this both RE1 and RE2 will provide that DC stability. Okay, but what you are getting advantage, in terms of gain, because here the gain would be dependent on this gain, means the gain would be this. You see this, it will be RC by means closely, it will or approximately it would be RC by RE1, not RC by RE1 plus RE2. That way you can improve the gain, but you can also get some stability.
Okay, sir. Understood.
Okay.
Yes,
Okay.
sir.
Okay, then thank you.
Thank you, sir.
Yes, thank you.